Long before there were animals or plants, there were builders. And before there were brains making decisions, there were, well, decisions being made. We're going to go all the way back to that incredible moment when chemistry became machinery, to the very origin of how life actually learned to build itself.
So right now, as you're watching this, inside every single one of your cells, there's this entire universe of tiny, tiny machines just furiously at work. I mean, they're copying your DNA, they're hauling cargo from one place to another, generating energy, they're even repairing damage. They move with this incredible sense of purpose, and they coordinate with each other. And the wildest part of all of this, every single one of them built itself.
And that right there is the central mystery. If there wasn't a blueprint, no engineer from the outside telling these molecules what to do, how on earth did this staggering level of complexity just appear? How did a bunch of non-living matter learn to build itself into the machinery of life?
Well, the whole journey starts with a really fundamental principle. It's actually one of the most elegant ideas in all of biology. The simple fact that a molecule's physical shape is what determines its job.
Okay, so picture this. You've got a long, floppy chain of atoms, like amino acids, and you just drop it into water. It doesn't need any instructions. Immediately, the laws of physics just take over. Some bits of the chain hate water, so they tuck themselves into the middle. Other parts are charged, so they either attract or repel each other. And in just milliseconds, the whole chain collapses on itself into a single, stable, three-dimensional shape. And here's the crucial part. That final shape isn't random at all. It's functional.
And this reveals a really profound idea. The instructions for how to build the machine are literally encoded directly into the sequence of its own parts. The blueprint isn't some separate document, it is the machine. If you could unfold it, it would just fold itself right back into the exact same functional shape, every single time.
This is the complete opposite of how we design things. As humans, we start with a goal, like I need a hammer, and then we design its shape to do that job. Nature works completely backwards. A random chain of atoms folds into a shape, and only then does that shape discover a function it just so happens to be good at. The function emerges from the form. And the functions these shapes can have are just incredible. Take myosin, for example. It's one of the little motor proteins in your muscles. It literally grabs onto another protein, changes its shape, and pulls, moving just 10 nanometers. Now that's a tiny, tiny step, but when you have trillions of them all working together, that's what lets you move your hand, or blink, or even pump your heart. It is literally chemistry becoming mechanical work.
But okay, a single machine, no matter how cool, isn't enough to create life. So next, we're going to see how these simple parts start to coordinate with each other and form these complex, self-regulating systems.
This is where it starts to get really, really clever. So once you have machines that can do work, they can start building other machines. Imagine machine A creates something that machine B needs to function. And then the thing that machine B makes, in turn, helps machine A work even better. Suddenly, you don't just have two separate machines, you have a self-sustaining feedback loop. The system itself starts promoting its own existence.
Now scale this up by the thousands, and what you get is metabolism. It's not just one process, it's this vast, interconnected economy of chemical reactions. Thousands of molecular machines all building stuff, breaking stuff down, redirecting molecules. And what's just wild is that it regulates itself. There's no CEO, no central command. The network just maintains its own balance through countless little local feedback loops.
Okay, but that brings up a pretty big problem. If you've got this brilliant little chemical network just floating around in the primordial soup, what's to stop all your carefully made products and useful machines from just drifting away? The system needs a boundary. It needs a wall. And once again, physics provides this amazing automatic solution. Lipid molecules, you see, have a kind of a split personality. They have a head that loves water and a tail that hates it. So if you drop a bunch of them in water, they spontaneously arrange themselves into a bubble, with all their tails hidden on the inside. No assembly required. A boundary just appears, creating a protocell with a distinct inside which concentrates all those useful reactions together.
So we have machines and we have systems, and they're inside a container. But there's one crucial piece still missing from the puzzle. We need a way to remember how to build the machines and then pass those instructions down. This is where information finally enters the story.
And this leads us to one of life's great paradoxes. See, in our modern cells, DNA stores all the blueprints, but it's totally inert. It can't do anything by itself.
It needs proteins to come and read it and build things. But to build those very proteins, you need the blueprints from the DNA. So which one came first? It's a classic chicken and egg problem.
Well, the most elegant solution seems to be a molecule that could do both jobs at once, RNA. Now, it's not as stable as DNA for storing information, and it's not as versatile as proteins for doing work, but it could do a decent job at both. This RNA World idea suggests that the earliest life was based on these molecular jacks of all trades, which solves that whole chicken and egg problem entirely.
Now, once you have a system of information that can be copied and can also make occasional mistakes or mutations, you get the final magical ingredient: evolution. And here's the thing to remember about evolution. It doesn't design things from scratch with some grand plan. It just tinkers. It works with whatever parts are already lying around. The bacterial flagellum is a perfect example of this tinkering process. I mean, it's an absolutely astonishing little molecular motor, but it wasn't invented in one go. Its parts were borrowed from other systems that were already there. The motor itself was repurposed from a protein pump. The propeller was modified from a grappling hook structure. Evolution just cobbled together a rotary engine from spare parts it found. And the results of this tinkering process are just staggering. A typical car engine, right, it wastes most of its energy as heat, so it only gets about 25% efficiency. These molecular motors, on the other hand, operating at the nanoscale, they can convert chemical energy into work with up to 80% efficiency. That's approaching the absolute limits of what's physically possible. And they're not just efficient, they are unbelievably precise. The machine that copies your DNA, called DNA polymerase, flies along at 1,000 letters per second, and it makes about 1 mistake per billion. To put that in perspective, that's like typing out the entire Encyclopedia Britannica thousands of times and making only a single typo. It's just insane. So let's just put it all together. You have these self-folding machines where shape gives them a function. These machines then form self-regulating networks. Those networks get enclosed by self-assembling membranes, and the entire system is guided by self-replicating information that allows it to evolve and get better. This gives us a whole new way to think about what life really is. Maybe it isn't some mysterious, unknowable spark. Maybe life is simply what you call it when molecular machinery reaches this incredible level of coordination, when chemistry organizes itself into a system that can sustain, repair, and replicate itself against the endless pull of chaos. The journey from just a single folding molecule all the way to you and me is almost incomprehensible. Matter, just following a few simple rules, learned to build machines. Then those machines learned to build systems. And those systems eventually built everything we see. It leaves you with this one final, really awe-inspiring question. If this is what matter has learned to do so far, what comes next?